my app file over here. So I think that's a good first stab at this thing, you know. I'll have to try to type up some of this stuff and see if it still makes sense once I go through it again, write it out, you know. I am curious about this integral on A cross A. What are its properties? You know, this integral that we defined here. I mean, I would like to say that the condition partial q partial w equal to partial p partial z, if that condition holds over an appropriate domain, that implies that this integral is path independent. That'd be nice.
Okay. Bear with me here. So we're saying this is real, right? Is that what we're assuming?
I think algebra values in there.
Is algebra?
P and Q are functions from A cross A to.
No, but what? Like, so are these also? Are these the variables they're acting on?
Yeah, it's Q at the pair. Q at z comma w. So that for fixed z and for fixed z and zeta, Q of z zeta is a particular A value, the number.
In the
Yeah.
It says here that the validity of the equality is the subject of exercise 58 from section 17.3.
Which where are you?
I'm on the MIT calculus 1 and several variables. So 17.3.
Come on, computer. It's booting.
Okay, I'm not. I think I find it. Chapter 18. What is this? 18.7.
So are we?
Page 860. It gives you a little thingy on the margins, and it says the validity of this equality subject to exercise 58, section 17.3. I'm trying to get a 17.3 now. What is this? 18.9.
All that exercise is to just calculate that those partial derivatives are equal.
Really?
Yeah, don't be fished in by that. That's just a calculation. That's just a hey, differentiate these, show they're equal problem. I believe.
Then how are they saying that holds for all?
Well, the point of this function, this example, is on a not simply connected domain, right? It's a punctured disk. 0 is missing. And for this one, y over x squared plus y squared, and then minus x over x squared plus y squared, it satisfies the relation that partial p partial y is equal to partial q partial x on the punctured disk. However, you cannot find a gradient function on the whole punctured disk for that. In other words, in fact, the theorem does not apply there because the topological condition of the domain has not been met. You know, that's a kind of interesting. Can we do example 5? Ooh. Ooh. Ooh, ooh, ooh. I don't, So,
What are Q mappings of?
so the
P and Q or A crossing it
So, by the way, the path independence here, it's got to be big. To prove path independence of this integral, given given the condition that partial q partial w is partial q partial z, like the argument is essentially going to be, well, if you're going to have it on a region which is nice enough to make that construction, and then no, that's not what I'm trying to say. Dang it. No. Oh, yep. This is an idiot. If you can rewrite this, right, as the gradient of a function, then you ought to be able to have Hey, there's a question. Do we have a fundamental theorem of calculus here?
In A cross A.
In A cross A, right? So here's my question is, if PQ, right, is equal to the gradient of, let's call it little f, then does that imply that the integral from, say, point, I need some notation here. Unfortunately, I've already used P and Q, which are my go-to endpoints. So let's say P1 to P2, a curve that goes from point 1 to point 2, right? So is this equal to f of P2 minus f of P1? What do you think?
that is the definition of our mean value theorem, right?
I mean, this is usually called the fundamental theorem of calculus for line integrals.
Oh yeah.
But in my current notation, don't be deceived, I'm asking a question about this integral that we just defined right above. Right. Excuse me. So, what do you think?
Math stack is not helping.
So we have integral, say from point 1 to point 2 in A cross A, right? So I'm using this notation for some curve at A cross A, right?
Mm-hmm.
And we've got a gradient of f dot dr. Now what does gradient of f mean?
It means you take the partials component-wise.
But in A cross A, we define this to mean
That.
it is partial f, partial z, partial f, partial w. Right?
Yeah.
And then we define this integral to mean what? This integral means you take the p component, which in this case is partial f, partial z, you evaluate it, the parameterization, multiply by dz dt. So this is the integral over, say, t1 to t2 of partial f, partial z at the point, the parameterization of the curve, right?
Mm-hmm.
And then times the z component of the parameterization dt. This is an algebra multiplication, of course. And then plus partial f, partial w at the parameterization dw dt. dt, right?
And then this should be able to commute right now that you have, unless, well, is this function algebra?
Yeah, so like to be more clear, this is z of t, well maybe it's not more clear, maybe it's less clear. It's z of t wt, this is also z of t wt.
Mm-hmm.
You know, and I'm using the notation, which is a little bit bad. So what I'm trying to point out here, is this is I believe I think we can, this is a chain rule. So I can rewrite this as the integral t1 to t2 of d dt of f of, z of t wt, or I can just write gamma t.
Oh, okay, no.
I'm claiming there is such a chain rule, we can prove it. And then this right here, f composed with gamma, is actually a mapping essentially from some subset of the reals. This subset, okay, to the algebra. See, f was a function from A cross A to A.
But these are two functions. How's that a chain rule though?
These are both A-valued functions. These are functions from z is a function, here z is a function from the reals to A.
Mm-hmm.
W is a function from the reals to A. This is actually its value, z of t and w t. So those are giving you a pair of, this is something in A cross A, which is why we're feeding it partial F, partial Z. But this, of course, is just the total derivative of F of gamma T, right?
Yeah.
So we're integrating a total derivative, it's,
Oh, yeah, those are familiar.
right, so by the, well, that changed, and whatever you want to call it, this is F of gamma of T2 minus F of gamma of T1. But of course, by construction of the parameterization of the path, that's F of P2 minus F of P1. In other words, yes, this integral plays nice with our definition of gradient in such a way that this integral has the fundamental theorem of calculus for line integrals in A cross A. It's what we hope for. Again, the big assumption here is that there.
I don't like, let me see this thing. I did not want to buy this ebook.
So thank you, MIT professor, for posting a PDF of this out-of-print calculus book. Yeah, when we stopped using it, it gone up to $377 in the bookstore. It's like, oh, curses, I guess we can't keep using it. It's such a good book.
See, the problem this guy says is that partial derivatives do not commute with integrals unless under very certain circumstances.
Mm-hmm.
Whereas derivatives can, in some sense.
No, you can commute an integral and a derivative given certain conditions on the integration.
Yeah. So,
But I didn't do that here. I mean, this is just chain rule followed by fundamental theorem of calculus for a valued function of a real variable. The theory of these kinds of things, like functions from the reals to the algebra, that's defined and discussed in the Introduction to Calculus paper in section 10. The way that works is you just integrate component-wise. For example, if you were going to integrate, here's one, like if you were going to integrate, say, e to the t plus cosine of t times, v2 over dt. So this would be, a function from the reals into the algebra. If you were to integrate that, say from 0 to 1, you just do the integral from 0 to 1 of e to the t plus v2 times the integral from 0 to 1 of cosine t dt. So it just works like that.
see, the problem I have here is that it doesn't look like a chain rule.
Oh, this one?
Yeah. Looks more like a product rule. If I can't think, because, well, this looks fine, so if it was a product rule, it'd probably look more like, So like you got this dz dx good, and you got this dw dt, but you know you need a z here, which if z stays constant, z doesn't change, and then here w doesn't change. So you know if you evaluate this, you no. Oh, I don't know, that doesn't work. I was trying to say that like, that it wouldn't matter because I think you get rid of those things. Oh wait, no, okay. What I was thinking is that like, if W held constant, you do this, and you get W dz dt. And that'll give you f gamma of d by the chain, by the product rule.
But F is not equal to Z times W.
That's not as true. It is P and Q.
F is, I don't know what F is. F
Yeah.
is just a function of Z and W. So, okay, so like to prove the chain rule, I'll write, just need to carve myself out a little space. I think I should do it over. I'll do it right in the middle here. Right about here. I think. All right, so. So we're considering, I'll start with ddt of f of gamma of t, yeah? Now here f is a function on A cross A to A, right? So our notation has been that as real variables, this has what? x11, x12, x1n, x21, x22, and so forth, right? These are the real variables on A cross A. Agree?
Yeah.
Okay. So remind me to unzoom the camera once we get done with this. Otherwise I will regret. So this is actually a function of x1 x2n, but you're setting this equal to, I mean, this is gamma of t. It's really gamma of t has 2n component functions of t, right? So I'm just going to say gamma of t equals to this, which is an abuse, right?
Yeah.
But that, if I write that, then I mean that each one of these is separately a function of t. But I'm also going to use those as the Cartesian variables of 2n dimensions, just like I did down here. I'm abusing z both as the variable and as a notation for the component function of gamma. I will engage in that same abuse here. So the chain rule, it is partial f, partial x11, dx11, dt. So this is just like the chain rule of calculus 3. It's Katie's last one. Now, let me just write this in a slightly different notation. You could also express this as the I'll say 2n dimensional gradient. I'll put a 2n here because I'm using that symbol in a different sense. But it's the 2n dimensional gradient of f evaluated at gamma of t, dot product with d gamma dt. Now this is a dot product of 2n dimensional vectors. That's what we have up here. Technically, every one of these is evaluated at gamma of t. That's just chain rule. The thing is, because we're assuming a differentiability in both senses in the second and the first slot, right? We can trade these for what? We can have partial fx11, right?
Times something.
This one becomes partial x11 times
dx12.
v2, right?
Yeah.
And this one pulls out of Vn, but we have a partial x11 on each one of those. And then that gets multiplied by what? By dx11 dt plus, v2 dx12 dt vn dx1n dt.
What do we do for these?
Very good. So for the other ones,
We plot the same song and dance, just add them together.
exactly, but this time it's partial
Partial x21.
x2, 2-1 times,
Yeah, same song.
but this time with 2's, x21 dt plus v2 dx22 dt vn dx, and again, I'm assuming that the identity is the first component. All right, but that is, well, first that's dfd, that's partial f partial z, right?
Mm-hmm.
And this is ddt of what?
Gamma t?
Well, yes, but, well, not quite. x11 plus v2 x12 plus vn x1n. This is literally z. It's a linear combination of the first n variables in the A cross A.
Yeah, you had it somewhere.
It was up there somewhere. I
Yeah.
erased it. I need more boards. We need more boards.
Yeah, and then same thing with that, yeah.
Same thing over here, except this one is partial f partial w.
W.
Exactly. And then this is ddt of x21 plus v2 x22 vn x2n. This is straight up w.
Yeah.
So what we have is partial f partial z dz dt plus partial f partial w dw dt if I drop the stars.
And so that means
And that is what I did. See,
Yeah.
that's why this is the derivative of the composite of f with the path on A cross A.
so when you're taking the derivative of algebra, you're taking the gradient. See, but this implies a gradient, doesn't it not? Because you're taking this with respect to z and this with respect to w.
I mean, it is also true. It is also very satisfying that this is, in our notation, the gradient of f over the
Yeah.
algebra,
Yeah.
dot product with,
Yeah.
so notice that the difference here. This is the dot product of two, there's too many twos here, but these are two component vectors in A. Each component is at A. Right? In contrast up here, this is the dot product of two n vectors.
Yeah.
So if n happened to be two-dimensional, this would be like, if A was two-dimensional, these would be four vectors over the reals. Whereas these would be 2 vectors. I mean, if you break them down further, these are that, right? It's just a kind of gathering of notation, but it also only makes sense in as much as we apply the Cauchy-Riemann equations, right? And the Cauchy-Riemann equations were mission critical to get from here to here. It is the Cauchy-Riemann equations, right? Like this transference of concept, it does not work. It does not work at all for a function of A cross A, which is not just having, you know, A derivatives existing in both ways.
Okay. And so if we have that, which is here, right? Now we're here.
Yeah.
So that means, one sec. Well, then what does f of P2 mean?
What this means, this is the theorem, right? If f vector, if you like, maybe I shouldn't even use that. If PQ, right,
Mm-hmm.
is equal to the gradient, I guess I can put enough. You know, some subset U, which is a subset of A cross A, right? Then the integral of P comma Q dot dr and is independent of half. On U, in the sense that, meaning if we have C1, which goes from P1 to P2, and we have C2, which also goes from P1 to P2, right? Then the integral over C1 of PQ dot dr is equal to the integral over C2 of P comma Q dot dr. Why is that? Because this thing we just proved, right? What's the deal? Well, this is the integral of the gradient, but so is this, right? So the significance is that both of these are just given by f of P2 minus f of P1. I mean, okay, so I'm not writing my proof writing my proof like an addle-brained high schooler with putting equals about things I'm trying to prove are equal. But the point is, the reason that these are equal is because the value of these integrals depends only on what the potential function little f does at the endpoints. So as long as the endpoints are shared, the difference of f at the endpoints is shared. So this is part, this is part of the story of conservative vector fields. So we've recovered part of the story of conservative vector fields on A cross A. Or the A-plane, or whatever you're going to call it. The actual value of f of P2, it doesn't have particular meaning. You can always take that function f and shift it by a constant and it still works. So like there's no absolute meaning to f. It's like a potential energy function. Does that make sense?
Okay, so if Q is a function evaluated at zeta, right? If we took the integral, okay. So could I rewrite Q like this? Q is some like gamma t. Like that.
No, why are you rating, oh, at z again?
Yeah.
I'm not sure. What are you getting at?
Or would it be better to write it like this?
Well, I mean, I guess the question is, what are you trying to get at here?
Right? What I'm trying to get at is that if we did that wouldn't work because what's W not in W? What does that even mean? What I was thinking is that what would I need to do? I need a partial x, so that would be a partial z. That if you also pulled this in, but like what's z?
Ooh.
I think I'm going to jibber jabber around.
Yeah, I don't know about moving derivatives in and outside the argument of z. Like
Because then I would say this is,
in Q rather.
this has the real, and so then I would switch it in here. Which, I don't know, yeah, but it's partial anyway, it doesn't matter.
It's the partial derivative and the integral that we can commute. Like, I don't have any technology to get myself like inside arguments of Q.
Yeah, but we can't prove that the integral and the partial derivative commute over an algebra.
That's the question. I think we can. But you're right, that's something that we need to kind of get our paws on, right? So, I mean, list of things to try to do carefully. One of them is to show that that thing I was just showing you in the book there, right?
Mm-hmm.
Can we adapt that argument or steal that argument plus like Cauchy-Riemann equation kind of thing to prove the partial derivatives commute for the on A cross A? Given appropriate conditions on the function of A cross A, can we do that? And also, how do we prove that the partial derivative and the integral, the partial integral, if you will, can commute given appropriate conditions on the integrand and its derivative? Now, I'll have to find a good proof of that for us to look at, because I don't know that right offhand, and I don't think we're going to find it in Salas and Hilly, because that's not.
Can you rewrite an integral as a summation of things?
You can, but I would wager that the proof is going to be along the lines of like. I mean, I guess that's a possibility.
Because if you could like. You could rewrite the integrals like.
See, but again, if it's not just the sum, it's not a finite sum you're dealing with, right? It's the limit as the partition goes to infinity that defines that integral,
Yeah.
But listen, I will look for our next meeting to try to find like a legitimate proof of that we can like work through. I might need to drive to UWA. The book I might need might be there.
In calculus, the Leibniz integral rule for differentiation under the integral sign is expressed. This is ugly.
So the proof probably goes something like this. The assumption is that the derivative is continuous. If the derivative is continuous on the integral, that means that it's bounded because the integral is over a closed interval. So the fact that that derivative is bounded means that you can essentially make that as small as you like relative to the size of the interval. And then on the flip side of things, like it usually ends up being something about the boundedness of the derivative paired with the fact that it's continuous means that continuous the continuity of the derivative bounds the derivative sense of the context here. And so then you can get a control over the size of that thing. And then you have to like compare that against the other thing, and then
so
it's an analysis thing. So
like if we have this
squeeze theorem kind of thing,
or something, right? What does a limit look like under the algebra? I'm just rewriting because this is essentially what an integral is, right? This part. You're taking, the way I remember integrals, at least, something to something, and some point A to B. If you do it off just like the rectangles, it's infinite sum.
There is a way of defining the integral over the algebra like that. That was my initial definition. We used it to prove the mammal theorem. And but again, you get into trouble because there's a question there because you have partial x and you've got a limit, so you can't exchange the partial derivative and the limit.
Okay.
Without like the theorem applying.
Could you exchange that? No, that's stupid.
Yeah, you can't exchange that because that limit actually is over the partition of y.
Yeah, and my other thing would be like, if this is a summation, this would be taking the limit of every single component, and that doesn't make sense to take the limit of every single component.
So I suggest we wait on that for the next meeting. Give me a chance to find like a good proof that we can, dig into.
I'll probably look into.
Yeah, as soon as I find it, I'll send it to you.
Yeah. I was gonna go home this Sunday because of Father's Day. So I was thinking about, and then I have a doctor's appointment on the 25th, which is that Friday. So.
So you want to meet like next Saturday?
Yeah, if you can.
Probably.
Okay. Yes.
All right, so I'll be looking for that. I think we have an hour left.
Yeah.
All right. Let me attempt to show you the other project we can work on.
Okay.
I think this is gonna work.
Yeah, same. I just think it's a matter of finding the definition or someone that's already done it.
And so that's good, but a couple things.
See, oh my bad. But the reason I think this would work too. It's just I feel like I'm kind of stuck on like this rigid definition set by this guy.
Oh, this is fine. Like this is independent of that story.
Yeah.
the commuting the integral and the partial derivative is what we need in order to show that this actually has partial f, partial f, partial w equal to q, was it? Or no, the get the p one, to get p to match up. We need the derivatives commute
and it spits out p of x something, to get rid of the q term.
Yeah.
That's all we need to get rid of the q term.
So there's that. Another thing that I think will be worth investigating, Audrey, is example 5. And I'm not going to do it right now. I'm just going to like talk about it so you have an idea.
Okay.
So the if we look at p comma q, and I should start giving the thing a name. I keep using pq as a means to avoid giving it a name. But anyway, the formula was this. It was basically z over z squared plus w squared, right? And minus w over z squared plus w squared. I think if I gotta check on that example 5. No, it's the w's on the first one and the z's on the second one. This is w.
Is the minus to the same?
And the minus is on this one, yeah. So I believe that you can show that partial p partial w is equal to partial q partial z, of course, for z squared plus w squared, what? Not equal to 0, right?
Is this the question from that theorem is coming from, that shows you sure?
This is sort of the warning that it's not enough. You can't just the simply connected thing. It's not just idle chit chat.
Yeah.
It matters. So in the real case, when you have x and y here instead of z and w, this is a vector field that it has a closed condition, and yet there does not exist a potential function on the punctured plane. Prove to you that that's the case. It's pretty simple. I think I've showed you this before, but I'll do it again. So here's the unit circle punctured, right? So if we're going to integrate,
Oh yeah, you can't because there's a discontinuity there.
But how's that flesh out here? Minus x dy over x squared plus y squared, right? And so, see, if there was a potential function for this, and you integrate around the loop, it should be 0 because you just pick a point, right? And that's your p1 and your p2, f of p1 minus f of p2 minus f of p1, 0.
Yeah.
So if this integral around the loop is non-zero, there cannot exist a potential function on the totality of the punctured plane. That's the argument. And this integral along the unit circle, right? So you just put x equal to cosine t, y equal to sine t, that's a parameterization of the thing, right? And so that's 1, and dx is minus sine t dt, dy is cosine t dt. So you look at this, you actually get integral from 0 to 2 pi, all around, and y dx gives us a minus sine squared, and minus x dy gives us a minus cosine squared. So this is literally minus dt over 1, which gives us minus 2 pi. All right? So I would say that the choice of signs in example 5 on page 859 is Salas and Hilly, like plus or minus signs, to my tastes, a little bit off. I would usually like to say x dy minus y dx so that I get a 2 pi here, just as a point of personal, Anyway, this is not equal to 0, obviously.
Yeah.
Therefore, this function, this vector field, cannot be expressed as the gradient, right? So there does not exist f such that gradient of f equal to, y over x squared plus y squared minus x over x squared plus y squared on R2 minus the origin, right? Also known as x comma y such that what? X squared plus y squared not equal to 0, right? X squared plus y squared not equal to 0 is just R2 with the origin deleted. So my question is, what happens to this example over the algebra, across the algebra? Of course, if we take the algebra to equal to the real numbers, this happens.
So my next question would be like, do I need to find, is it sufficient enough to find an algebra that this isn't the case? Or does it have to be a generalized thing, like if I have an outgrowth?
Could be, I mean, I'm just interested in what we can say. I have no idea, I'm just throwing it out there.
Okay.
I literally don't have any idea at the moment. Except, like I said, if we choose A equal to R.
Yeah. Yeah, because like I feel like there's something where like a zero divisor plays out and then you pop out a unit, like you pop out a hole.
I think that, I mean, this may be an artifact of the two-dimensionality.
Mm-hmm.
It may be the fact that this is in R cross R, which is, R2. So when we delete the point, that gets us a space which is not simply connected because we can't deform past the loop, right?
Yeah.
So my intuition, my rough intuition, is that it kind of depends on what z squared plus w squared not equal to 0 looks like. What is that set inside A cross A? See, if that set, z squared plus w squared not equal to 0, if it was large enough to make the resulting region in A cross A not simply connected, then I have a suspicion that something similar happens to the real case. However, if z squared plus w squared not equal to 0, if that leaves you with a space that is large enough to deform loops, I tend to believe that we can construct a potential function that returns that vector field p comma q in the purple at the top of the board as the gradient of that potential function. Because if we have more than 2 dimensions, we can work our way around holes. However, in 3 dimensions, if we have an axis, if we lose an axis, we can't move our way around an axis, You get something stuck on a pole that goes infinitely far up and down. You can't move that hoop off the pole. You got no way to slide it over, Hola, Batman. So anyway, that was my other kind of related, and also just more generally, trying to understand that 3-part theorem in the paper and its adaptation to the plane A cross A. I'm also, by the way, I will do my best to find a better proof of the potential construction, not just for a rectangular region, but for like a simply connected region. Okay, I'll try to find a better proof of that for us to look at, because there's something I'm forgetting. I'll have to look. And besides all that, maybe just pick, maybe just try some integrals over algebras just to get a better sense of how functions integrate, what it looks like,
Yeah.
Because it's a little bit surprising actually how things work or don't work.
Yeah, I got stuck pretty fast.
Yeah, I don't.
Because I just tried to do HQ,
Mm-hmm.
and you get this. I don't know if that's 0 to
you're just doing on H cross H?
Yeah.
So can you find, so the question is, can you find, so your question is, can you find non-zero solutions to z squared plus w squared equals to 0, where z and w are hyperbolic quantities? Is it possible to have non-zero solutions to that in this question?
Yeah. Oh.
I'm gonna erase this. Probably not,
No, probably not.
because there's like there's no I in H. So, I mean, in some sense, I need to have like a square that gives me a negative, and something that can do that. It's like an imaginary unit, and I know what. But of course, you can. This is what? This is like x squared plus y squared plus u squared plus v squared plus j, well, 2j times xy plus uv, something like that, equal to 0. So you're looking at x squared plus y squared plus u squared plus v squared equal to 0, and xy plus uv equal to 0. Well, this right here, game over, man.
Yeah.
That forces all of them to be 0. Therefore, the only solution to v squared plus w squared in h cross h is 0. Now in H3 cross H3, there is something there. So instead of doing H3, let's just be like manifestly like stupid about it and say A is R cross C, right? That's what H3 is, up to isomorphism.
Yeah.
So there, if you look at, let's say x comma z squared plus y comma w squared equal to 0, that would be like, this is my z squared plus w squared in R cross C, and that of course would give you x squared plus y squared comma z squared plus w squared. Oh man, that's not the kind of C I'm looking for. See, I still get x squared plus y squared equals to 0, z squared plus w squared. I still just get 0. That again, only got 0. It's just eliminating 0. So it's like kind of like H3 cross H3. It's like R6 with the origin deleted.
Null numbers? No, but there's nothing like that isomorphics.
Null numbers. Not a bad choice. Gamma. So there we're looking at z squared plus w squared. Let's see here, to expand that, that's x plus epsilon y. I'll use u and v.
Yeah.
U plus epsilon v squared.
You already get 2 zeros off the bat. Are you? Yeah. So x
Yeah.
squared, the y cancels xy. You get epsilon xy, 2 epsilon xy, right?
Oh, thank you, 2 epsilon xy, yeah.
Same thing.
So we get x squared plus u squared equal to 0, and xy plus uv equal to 0. This tells me x equal to u equal to 0. And, oh, free! This is for free in the sense that this is so this
Yeah.
says solved and no condition, right?
Yeah.
On what?
On y